So welcome everyone. I'm Enrica Dechan and I'm a senior scientist at CMCC. And today it's a great pleasure for me to introduce our speaker, Professor Ian Siu Wing. Professor Ian Siu Wing is also a recipient of the CMCC Senior Bassi Fellowship. And with this fellowship, you will be visiting our institute, the European Institute on Economics and the Environment in Venice, until mid-November, and he will be back again in spring. So those who are around are very welcome to get in touch with Ian and try to meet up with him. Ian Siu Wing is a professor in the Department of Earth and Environment at Boston University, where he conducts research and teaching on the economics analysis of energy and the environment, with an emphasis on climate change and computational modeling methods and tools. Much of his work has been focusing on articulating the linkages between computational models, empirical models, but also more like engineering, bottom-up models, in the domain of energy system, agro ecosystems, and natural hazards, with the goal of better characterizing the impact of climate change and also of climate change policies. His work has been supported by several organizations and agencies, especially in the US, but not only. For example, he's been receiving support by the US Department of Energy, the US EPA, the Geological Survey, the National Institute of Food and Agriculture, the National Science Foundation, but also Wellcome Trust, more at the international level. He has also been a member of important advisory groups and panels, including the IPCC, Assessment Report 5, and the US Third National Climate Assessment. Now, before giving the floor to our speaker, I would like to share some words about the hosting institution, CMCC. CMCC Foundation, the Euro-Mediterranean Center on Climate Change, is an international independent multidisciplinary research center that studies the interaction between climate change and the society. It is a reference point in the climate change domain, and it has ongoing partnership with institutions, centers, and networks in more than 70 countries around the world. The missions of CMCC is to develop and advance models from climate to physical, biophysical, and socioeconomic models, with the goal of supporting science-driven adaptation and mitigation action. We try to deliver scientific insights that are needed for a successful transition to a sustainable future, mostly through foresight and quantitative methods. To do this, we rely on a research infrastructure that is articulated in 3 multidisciplinary research institutes, in 4 strategic programs, and it also relies on a powerful computing infrastructure and 2 specialized centers on digital innovation. A bit more specifically, our research institutes include the Institution for Earth and System Prediction, the Institution for Climate Resilience, and the European Institute on Economics and the Environment, which is hosting the lecture today. The 4 strategic programs essentially try to address the main challenges that we face in an environmental and social context characterized by a changing climate, and it does so by bringing together expertise from the different research institutes. And lastly, some facilities and infrastructure that we have and that enable us to do this type of work. Coming to the series of this CMCC lecture webinar series, the intent is really to promote scientific dialogue and also foster insightful debate on frontier research topics. And on CMCC website, you can find the previous lectures that have been delivered. All of them will be recorded, have been recorded, and also the lecture of today will be available online. Now it's really almost time to give the floor to Ian. Just a couple of announcements before doing that. We have, as I said, a record number of attendees. So we have hundreds of people online, literally. So probably it will be difficult to handle all the questions, although we'll try to do our best. The interaction will take place through the Q&A box. So you can type there your questions. We will try to filter them and have a discussion informed by those questions. The question will also be recorded, and Professor Sue Wing is available to get back to you either in Venice, if you are around. We will also be visiting Milan on November 6th, or also online by email. And now it's really time for Ian to get started with his presentation. So Ian, thank you very much for your availability, and I look forward to your presentation. Now you should be able to share your screen.
Thank you so much, Professor Dechan, for those very wonderful remarks, and thank you for the introduction. And thank you to CMCC first for recognizing me with the Bassi Fellowship, and second for their wonderful hospitality in Venice, bringing me to Europe. Today, what I wanted to talk about was economic modeling of climate change impacts, and talk a little bit about trends and some new directions for modeling. The structure of this talk is going to be in 4 pieces. There's some introduction and motivation. We're going to talk a little bit about models. So I debated and went back and forth, and I think it's worth doing a little bit of a technical presentation and to show some preliminary results from moderately novel type of modeling in order to catalyze a discussion about a research agenda and potential new directions. And so to motivate, this is how I think about climate change, and particularly one thorny aspect of climate change, with a little bit of humor, but underneath it is deadly serious. It is climate-driven extreme events. And to the extent that they are surprising versus not surprising, my introductory slide had images from Porto Garibaldi flooding that occurred on the 5th of October this year. And we do here live in Venice, and so that is very much at risk for extreme events due to sea level rise. And so in this slide, just to go through the cast of characters, you have from the left Asok, who is a forward-looking intern at the organization of the main protagonist. In the middle, Dilbert, who is a myopic project manager. And then on the right, there's Wally, who is a hapless engineer. And I like this cartoon because it drives home the point that there are heterogeneous agents who are linked by commodity trade, investment, migration, social interactions. And the project that brings them together is the project of sustainable macroeconomic growth. And we can think of this as the archetypes of agents in the world and in Europe who confront the issue of climate risks. And the climate risks are shown by Dilbert's little cloud of doom that in the second panel zaps hapless Wally. Those zaps we're learning a whole lot more about. But in terms of specifically extreme events, we still do not have a good understanding of the location, the timing, their intensity, the interval of recurrence. There's a lot of spatial and temporal heterogeneity, and there's a lot of uncertainty given the different types of events. But new European projects, the CRU project, JRC's Peseta 5, they are generating ever more fine spatial and temporal impacts, which, challenge the current generation of IAMs. And so it raises the question, what trends in integrated assessment modeling could enable us to confront these challenges, and what investments in model development could yield the largest improvements therein. And so this, raises two research questions. One, sort of a question of, if extreme events occur, how might damaged and undamaged agents optimally allocate ex-post reconstruction investment? And how would they do so under different assumptions of myopia, not seeing the future, perfect foresight, perfectly foreseeing the future, or what I'll get to at the end of the talk, more interesting, something in between those two goalposts. And this is the question of, can Asok and Dilbert pool their resources to get poor Wally back up on his feet? And how would that happen? And how would we model such a thing? And that then catalyzes a longer run research agenda, which is, how do regional agents foresee the risks of future events? How can we tractably model their expectations and integrate them into integrated assessment models? And how might those expectations interact with uncertainty to incentivize precautionary investment and adaptation, but also potentially foster disinvestment and abandonment and retreat? And why would they do so? Big questions, thorny questions, how to make progress. Let's look at some other trends that have happened. So traditionally, computational general equilibrium, or CGE models of the type that I'm most familiar with and work most with, tend to resolve relatively few highly aggregated regions and incorporate fine scale impacts through aggregating them up, but that leads to potential biases. There has been a trend to reverse this by pushing these models down to very fine levels, and I've cited two pieces of work by CMCC researchers that have disaggregated economies out to the European NUTS 2 level, and they provide the capability to model the effects of detailed shocks. However, the computational demands of doing so mean that they have to retain a recursive dynamic structure, a fixed stepping through time of a sequence of economic equilibria. And what that means is that impacts are not foreseen, they're always a surprise, and there's no meaningful reconstruction because investment behavior is fixed in each period. If we want to get look ahead, the computational cost of intertemporal equilibrium means that we cannot also get geographic detail. It's just too computationally difficult. And this leads to a trend in the economics literature that is burgeoning right now, which is the use of quantitative spatial models that combine high resolution and forward-looking behavior. However, in order to do so, these sorts of models, it turns out, sacrifice key features that would facilitate direct incorporation of the kinds of exogenous shocks that are coming from process models, or easily through empirical studies. The first, Cruz and Rossi-Hansberg, models the global economy on a 1-degree grid out to the year 2400. But in order to do so, it doesn't have any explicit dynamics of capital. Accumulation is incorporated into the evolution of productivity that drives regional economies on a grid cell forward. And that poses a challenge to modeling punctuated extreme events. In particular, temperature affects grid cell distributions of consumers' amenities and producers' productivities. And this is an idea that has been picked up and advanced further by another paper, Bilal and Rossi-Hansberg, who have a very sophisticated, very neat multi-agent approximate dynamic programming model of 3,000 United States counties out to the year 2100. And the trick to make this go is twofold. First, you have spatially resolved dynamics of investment that accumulates capital and migration that determines labor supplies. But the decisions to invest and to migrate are formulated as first-order approximations to the Hamilton-Jacobi-Bellman dynamic programming equation. And the distributions of impacts on productivity, amenities, capital depreciations are really reduced form to a function of temperature perturbations. And so in this scheme, it's unclear how to introduce exogenous shocks of the kind that we're familiar with in the integrated assessment world. The third trend is that as we drive down toward the scale at which impacts and extreme events will be felt by the people who are subjected to them, we intersect with another class of literatures, which are economic modeling of disasters. And this is typically from the regional science domain. And this literature has heretofore looked at the recovery from and resilience to singular extreme events that trigger business interruption via damage to the capital stock, to transitory labor supplies, to productivity. And here the idea is that there's very little recurrence. The factor endowment destruction shifts the regional economy's production possibility frontier inward. And if there's no possibility of trade, there's no possibility other than discrete policies of inflow of resources from undamaged areas. And so damaged economies, capital stocks, output, consumption, and investment are permanently lowered relative to some no-shock baseline. And that means that sufficiently large shocks can cause a death spiral whereby investment as a function of output is no longer large enough to cover the depreciation through wear and tear and damage of the capital stock. And you get a permanent decline spiral where the economy crashes to zero. We tend not to see that in real life. In reality, we observe greater than baseline investment for reconstruction. And that means resilience on the one hand for impacted microregions. But on the other, it means transmission of risk to non-impacted regions where those undertake opportunity costs and give up investment growth of their capital and output in order that the impacted microregions might continue to grow. How do we model this? Well, it turns out that recent approaches have developed fast and computationally tractable primal approximations to some full intertemporal general equilibrium problem. And my paper in 2023 is the image shown on the right. Panel B shows investment rising after a shock, which happens to be an earthquake in California. And so the new frontier of this that I'll talk to you all about today is how to deal with recurrent disasters and spatial variation therein. And so let's go and do some modeling. How models like this are set up is that there is a criterion and objective which is sought to be maximized. And in an economic model called a Ramsey model, there are multiple regions, each with representative agents who consume and they derive felicity or well-being from consumption. And the objective that the model seeks to pursue is some weighted average of those where you average over time by discounting, treating dollars closer to today as more valuable than dollars in the far future, and weighting over space to provide some singular value of intertemporal well-being. The individual regional utilities are developed as a function of regional consumption, and consumption has to be balanced against investment and the use of output for generating more output in the future. And then what generates the resources to finance consumption, investment, and intermediates is a combination of, in each region, of goods and services that are produced domestically and those imported from abroad. The domestic goods are in turn produced from labor, capital, and intermediates and are subject to productivity advances, most of which we can easily model as improvements in the productivity of labor. And in turn, output is partitioned between domestic uses and exports to the rest of the world. We can then use this to link different regional models through trade. And in this particular example, we use a simplified specification of trade from an early paper in 1969, whereby regions export into microregions export into a macro-regional pool. And from that pool, individual microregions withdraw imports. Finally, the system is closed by sets of accumulation of capital in each region, regional capital stocks. And where the introduction to this talk comes in is that one can model shocks to capital caused by extreme events, and one can model them in two ways. On the left, a shock foresees the cloud of doom. And so with that foresight, one can approximate a shock's decision-making by looking at the optimal intertemporal plan of this economy based on the entire sequence of projected shocks out into the future, as if the future were perfectly foreseen. One can also model on the right Dilbert's behavior as someone who is myopic. He will not foresee the future, but he can still optimally recover, and he'll follow an intertemporal plan that assumes a one-off initial shock. The cloud of doom zaps somebody, but that will never happen again. And so assuming that there's no subsequent damage, but one can see the damage contemporaneously, and that involves a perturbation to initial capital and a plan for reconstruction as if everything will go well, which is what the regional science literature, much of the regional science literature, is predicated on. The latter algorithm I have chosen to develop and push forward, and I have given it a name, an adaptive rolling intertemporal plan, because what happens is that there is initial capital that's shocked by the effect of a natural hazard or an extreme event. And that can be solved for in plan time using the intertemporal model just described. And that solution then constitutes the optimal decision to be made in calendar time in its first period. And from the first period of the forecast model, one can then update variables like the capital stock and production and other things, and step forward in calendar time until the next period hits, and unanticipated shocks might hit there too. And so one can recursively solve for the trajectories of multiple economies by iterating back and forth between calendar time and plan time, calendar time and plan time, stepping through. I quantify this model using benchmark production parameters computed using a data set from the Joint Research Commission of the European Union, and other data from Eurostat, along with specific functional forms and other parameters from my own work and others in this area, particularly Yongyang Kai and Judd. I focus in this work on the destruction of capital from something we know is going to recur and something that we know will get worse over time, which is sea level rise. And I use estimates from the COACH project, specifically the work package results from Linky et al. 2021. And I focus on a large shock, SSP5, RCP 8.5, flood damage costs only, not reconstruction costs, because I want the model to compute the optimal reallocation of investment. And of this, about half of the 235 NUTS2 microregions in Europe are going to be affected, and most of them on the 2060 to 2075 timeframe. I study 3 scenarios, and those 3 are the static model, which approximates the kind of things that recursive dynamic computational general equilibrium models would do, just looping through time and sequentially accumulating capital according to a fixed savings rule, where sea level rises are a surprise and agents don't change their behavior at all. And this equilibrium, each of those equilibria takes about 40 seconds to solve on an Intel Core i9 laptop. A perfect foresight equilibrium, where the full sequence of shocks is foreseen, takes about 10 minutes to solve. And then finally, the adaptive rolling plan algorithm, where you loop through time periods and you solve for welfare maximizing if, investment allocations, but on a somewhat shorter compressed horizon of 25 years, takes about 1 hour to solve on an I9. So it's computationally efficient. It gets us answers, and let's see what some of those answers might be. The first thing to do is I'm going to show you a little movie of what the evolution of shocks will look like relative to the capital stock in the model baselines. And I do this because each of these models isn't the same and they have slightly different baseline equilibria. But as we step through time, we can see very, very similar patterns of impact. Redder, pinker colors show more severe impacts. So as we step through time, we see as we hit the 2050s, in particular places like the Veneto and Latvia are affected, as well as the Atlantic coast of France and Portugal and Denmark in the Baltics. If we look now at how the capital stock is actually affected, how accumulating capital deviates from its baseline state of the world, we see something very different. So in this graph, the light to dark blue colors are negative values. And what those negative values mean is negative losses. So losses are to the right, gains are to the left, and what that means is that the values in a counterfactual simulation with sea level rise are higher than those, more than those that would obtain in the baseline. And immediately what you see is that under perfect foresight, as early as 2035, because agents in the model are foreseeing that sea level rise will get worse, costs will get worse, and capital stock destruction will get worse, moving in with the production possibility frontier of the economy, they want to invest more earlier in the horizon to build up a stock of capital because they know that it will be destroyed. Moreover, the other thing that you see as you step through time is that the losses are more widely spread. And this is the opportunity cost of foregoing consumption to invest more and build a capital stock and make more output, even in places that are not affected by sea level rise, even places that are inland, because the agents who face direct shocks and the agents who are indirectly impacted are linked by trade. What we see is that this buildup is ultimately won over by the impact of the sea level rise shock. So the sea level rise shock undoes the effect of capital accumulation. And we can see the effect through micro-regional investment dynamics here. In the static alternative, everything just declines. This is the idea of the death spiral. And where I sit at the edge of the Veneto, this is really cause for concern because you have much lower investment because you have lower output. Contrast that with the other end of the continuum, perfect foresight, foreseeing large impacts at the end of the simulation horizon prompts much larger investment in places that are very severely damaged, up to 50–60% more investment relative to baseline, peaking toward the middle of the simulation horizon. The rolling plan shoots between these two goalposts and is much noisier because the recursive structure reallocates investment, but doesn't look ahead to see how bad future sea level can be. And so while retaining the structure of the perfect foresight equilibrium, the values of the amplification of investment are much attenuated. We can see the same thing or similar patterns through output. In a static case, because of the fixed savings investment rule, output just declines. But with perfect foresight, output actually increases slightly toward the middle of of the simulation horizon, the blue being unaffected, nominally unaffected areas, and the red being affected areas. While rolling plan shares some of the impacts of some of the behavior, of the static model, but again is very much attenuated, and we don't see output rising relative to baseline. Though we do see some of the patterns of foresight, but largely attenuated. We can also use such a model to explore ideas seen in the regional science literature of resilience. Here, what we plot is the instantaneous loss of utility, the loss of welfare or felicity of well-being based on consumption in any instant of time against how much capital would be reduced by the sea level rise shock. For those regions, the micro-regions that are impacted by sea level rise alone. And here, to the left of the 45-degree line, we can make statements that are rather cavalier and heuristic that, under the static and the rolling plan models, many regions would seem to be resilient simply because they face a smaller utility loss than the loss of capital, meaning that substitution across space or among inputs to production or reallocating output amongst consumption and investment and intermediates leads to a muting of the initial shock. However, one has to be careful with that sort of inference, because in the perfect foresight model, what we see is nominally you don't seem to observe the same sort of resilience. There are many more affected regions that have reductions in welfare that are larger than the capital stock loss that they will face, especially earlier in the horizon. But what this tells us is that you have to be careful with your criteria in these sorts of repeated recurring shock cases, because the baselines of these models are different. And indeed, models like this, their criteria are not to minimize losses. The criteria is merely to make investment such that utility is maximized. Utility is as big as possible. And indeed, even facing the shocks, the level of utility under perfect foresight is larger than the levels of utility in either the static or the rolling plan cases. There are also regional dynamics to be explored. Since this work is new and hot off the press, this is work that is ongoing. Here, the green represents Veneto. The orange represents Ceuta. And the purple represents Latvia. And so why the model in particular chooses to allocate investment in that way is something that we are in the process of interrogating. We can also explore the flip side of resilience, which is the transmission of risk, looking at areas that are not on the coast, that do not face the effects of sea level rise. And what we see is that there are much larger welfare losses in undamaged microregions, undamaged NUTS 2, under the perfect foresight equilibrium. And that if we think of perfect foresight, the green, and static, the red, as the goalposts, even the rolling plan is much closer to the right-hand side static goalpost. And that indicates that the key ingredient is foresight. The key ingredient that really shifts behavior is foresight. Another aspect is that when one looks at the welfare losses incurred in European capitals, France, Madrid, Berlin, big cities, they're smaller than the welfare losses than the neighboring NUTS 2 that are inland from the Veneto, which suffers really big losses. We are still exploring why this is the case, but I would say that there's nothing in the model that predestines this alternative. This all emerges out of the structure. It's an emergent property of the structure of the calibration data used to solve this model. And so that's something that we want to look into and understand more what the model is doing. in that vein, if I push on these ideas, I want to spend the last part of the talk discussing a few potential directions that this type of modeling work can potentially catalyze, and with the hope of sparking some imagination among the group. The first is to recognize the tremendous amount of work that has already been undertaken to spatialize computational general equilibrium models in CMCC and with collaborators, and to assure everyone here that I see the work I'm presenting today as entirely complementary to and synergistic with that effort. And if I go back to the rolling plan algorithm, I can pinpoint exactly why. The recursive structure of the ARIP algorithm means that we step through calendar time. But because we step through calendar time in a loop, that means at each step, we have the capability to do whatever we want. And so if it's computationally tractable enough, why not embed the CGA modeling work that is already occurring here? And here we have the opportunity to pursue a novel approach to an established paradigm of intertemporal modeling, whereby we solve a sequence of detailed static models that are consistent with intertemporal dynamics by setting the boundary conditions at each period consistent with the evolving factor endowments, the capital net of shocks, and the optimal plan investment that come from the dynamic model that I elaborated earlier. And the question is, what kind of results come from that, where we're now imposing in a CGE framework optimal recovery investment? And this is work in progress at the international level. Computational experiments with the Phoenix model for a US EPA study on modeling macroeconomic implications of climate change. Watch this space. I'll have results to report at the end of November. A second direction is climate change-induced migration. We have seen how reallocation of investment gives rise to recursive one step behind, one step delayed mobility of capital in response to climate shocks. Well, there's an opportunity to do something similar with fine-scaled mobility of labor as well. Labor in the results that I showed are fixed in place, but it need not be, as Bilal and Rossi Hansberg in their NBER working paper emphasize. We can compute, in particular, how labor would move around in response to a utility that we are solving for in the dynamic model. And that enables interregional reallocation to arbitrage utility differentials amongst nuts too. So if, as in Bilal and Rossi Hansberg, we can develop empirically a migration elasticity, then we can develop a simple gravity formulation where you have in each place natural increase, but that's balanced by immigration from other nuts to regions based on their utility relative to the utility of others, and others potentially donate labor, versus symmetrically an opposite outmigration, emigration to other nuts too, based on utility differentials there. And so the stretch goal for this type of work, even though that something like this, coupled with some empirical analysis, could be done fairly quickly, fairly easily. The stretch goal is that thinking along these lines really opens the door to opening this model up to introducing multiple consumers. And in particular, if we think about differential migration amongst the young, amongst workers, and amongst the elderly, we can very easily step to a situation where we now have endogenous dynamics of population and endogenous emergence of demographic structure in response to climate shocks. And I think this is a very, very important basis for planning. A third extension is to simulate multiple or compounding climate impacts. And I sort of moving up the supply curve, as it were, a metaphor from economics, going from easy to hard, been initiatives that we could take. So thinking about projects like PRIN and ACREO, we can take empirically derived shocks, computed and constructed at aggregate NUTS 2 levels for labor productivity, total factor productivity, and non-market impacts such as mortality, which I will work on as my project as a Bassi Fellow. And we can integrate them directly into this model as it stands right now. More challenging is to understand shocks that would be differentiated across and specific to different types of sectors. For instance, crop yields, which is another set of work that I'm involved in, and energy demand, which many of my colleagues here in Venice have been working on. There, we need to introduce sectoral structure into the planning model to elaborate the intersection between regions and input-output structure, but that is going to itself introduce attendant costs of complexity of the model and runtime. And it also creates an opportunity to link to Dr. Standardi's work on extending CGE models spatially. Finally, a stretch goal would be to think about not simply introducing multiple sectors, but have multiple sectors have sector-specific capital. And this is a really computationally challenging problem, but I foresee that it is not impossible given modern resources. And this is work by Professor Borsello and colleagues with a NUTS 2 CG model that resolves a bunch of different sectors, but some thinking expansively and somewhat differently from that. A focus given that what provides the resources in this model for additional investment is trade, to slightly reorient the focus to distinguish tradables, facilitating arbitrage spatially or shocks to output, and non-tradables, in particular housing capital, which is fixed in place and which has to be consumed by regional agents who are in place and can only really move around with low frequency once those agents themselves are mobile with migration. In particular, there's a famous theorem called the magnification effect. And so we would expect output that's based on fixed capital that won't move easily to suffer the consequences of the shock much more severely in terms of the decline in output. And that in itself will introduce other different types of dynamics into the model. Finally, I'd like to talk about a class of work or a part of the agenda which is really interactive and is trying to use the model to catalyze our thinking about uncertainty and about forecasting uncertain climate shocks. We've seen that perfect foresight and myopia are rather unrealistic extrema of a continuum, hence motivating the ARIP approach. And we've also seen that in the preliminary results I've presented, uncertainty has been sidestepped. In each period, sea level loss is a surprise, and reconstruction investment allocation doesn't foresee any shocks in the future. And that optimal reconstruction is relatively similar to the case of myopia, which means that the important thing that is driving dynamics is the degree to which agents foresee future losses. How do we get that critical ingredient? Well, this catalyzes a whole set of thinking about empirically grounded distribution of agents' perceptions of future risks. And I want to emphasize that this is not traditional impact projections, though those will certainly prove useful. Rather, it's an understanding of how agents construct conjectures of losses on different time horizons due to rare extreme events that they have a sense will become more severe and more frequent. And so it's different from an old paper by Robert Barrow that claims that we would be willing to give up 20% of our GDP to avoid a catastrophic rare event, or Lonsek et al.'s Nature Climate Change paper, which said, well, we would want to invest in abatement very stringently to avoid a climate tipping point. If agents don't really care about whether or not the climate tips, but they are developing ideas about, well, what will be the impact on they themselves, then we can think of expected future losses as a function of their own beliefs, their experience of their own and their neighbors' losses, and some way in which they might be incorporating evolving scientific evidence. There's papers on each of these things, but they haven't been synthesized and they haven't been brought together in a way that facilitates their integration into modeling. And I think those are two strands of research over the long term that have the potential to be hugely generative. And in particular, I'm thinking like about papers like Derek Lemoyne's NBER working paper, a new paper on the redefinition of seismic zones in the Naples caldera, and a paper that looks at charitable giving in the aftermath of UK flooding. We have lots of examples of salience, but the thing is to come up with tractable representations, that function f, which is currently an unknown. And then there's the question of, when we have that, how do we prepare that for integration into models, translating expectations into subjective distributions of shocks, a la Bill Allen, Rossi Hansberg, or DSGE literature by Engenkara at University of Sussex. And finally, that work can proceed in parallel with more modeling, because in particular, we have a good understanding from a recent paper by Young-Yang Kai and Ken Judd on how one can parallelize dynamic models in this sort of rolling plan type of framework to continue decoupling plan time expectations from calendar time unanticipating shocks, and through uncertainty modeling multiple dynamic futures at the same time at each step in parallel using high performance computing resources, and then combining them to recover the optimal period T investment policy using a certainty equivalent approximate dynamic program. And so these are only a few of the ideas that I might have. Hopefully I'm able to engage with folks, and I see that my time is waning fast. And so to be able to take questions, I'm gonna say thanks, and I'm gonna end with the slide that's a very, very famous painting that teaches us a little bit of humility, because we are all the drunk folks who are looking for their keys out in the darkness, but where we search is under the light of data, model results, and insights. And hopefully the kinds of things that I've talked to you about today can hopefully illuminate a little bit more corners of the darkness. Thanks.
Thank you, Professor Siu Wing. Thank you very much for this enlightening presentation. We do have about 10 minutes for having a short discussion around some of the questions that were posed by participants through the chat. And actually, more questions are coming as I speak. So let me try to guide the discussion on the basis of some of the questions. So let's say first, talking about the model, so more technical questions. There were some questions. Some people ask whether you could explain a bit better what are the transmission channels of the impacts across regions. Is it that related to the capital market? Is it related to transfers of any sort? I guess this also relates to a question, what are the assumptions with respect to capital mobility across regions? So this is the first.
So that very, very good, because this cuts to the heart of what gives the results. So I have tried very carefully in the model to tie my own hands. So if you look at the quantitative economics paper by Ken Judd and Young-Yang Kai, That is a multi-regional model, multi-regional growth model with an integrated capital market. And so that means everybody's production adds up together and gives everybody's consumption and everybody's investment all at once. And I've tried hard not to do that. So the only thing that allows in this model for transmission of the shock is one, changes in investment over time, and two, changes in trade amongst regions. Once capital is subject to the shock, makes output, and that output is reallocated between consumption, investment, intermediates, and exports and imports reallocate across regions, that's the only mechanism. Okay, because many mechanisms simultaneously means it's an equifinality. You can't really say. So trade is really the only mechanism in this model that quite deliberately moves resources around.
Thank you. Then we received a set of questions that somehow were relating to, let's say, more the type of shocks that you have been considering. So you've been focusing on sea level rise, which is like a slow changing impact, and also can be, let's say, more easily anticipated compared to other extreme events. So the questions that I would ask is this model suitable also to study like more extreme events, which are also short-living and more unexpected? Does time resolution of the model play a role? Because we had a lot of discussion about the spatial resolution, but not so much about the time. Is that relevant? Maybe not. What's your opinion on this?
It is quite relevant, and we would get different results if we go more granular in time. So in my 2023 paper with Adam Rose and Ann Wine and Dan Way, what we did was, after an earthquake strikes with California, we used a very similar model to look at the dynamics of reconstruction on a 6-month time step. So we went to half-yearly intervals. Essentially, you divide your economic quantities in the calibration data set by 2, and you recalibrate the model and you solve on a much granular time step. That will provide more fine-grained responses to short-lived, punctuated extreme events, because there you can see, unlike in the annualized coach results, you can see zeros, right? So you will have negative shocks, nothing happens, and then another negative shock might happen somewhere else or something like that. So granular in space and granular in time. Thank you all for the question. That is exactly the direction in which I want to go. But the more fine-grained you get, the larger, particularly for a perfect foresight equilibrium, the larger the problem of equilibrium that must be solved, the more computationally challenging it becomes, and the longer you have to wait to get your answer. But we can move from, say 10 minutes to 30 or 40 minutes with quadratic convergence, and we can see what a finer time scale with gaps might look like.
Thank you. And I guess this also relates to another question that, another participant was asking whether these type of models can handle multiple shocks hitting the same area.
I actually would love to explore multiple shocks hitting the same area, because that is exactly what's going to happen. And as we saw with the tragedy in the Texas Hill Country earlier this summer, individuals at fine spatial scale have a very imperfect understanding of the worst case. They have a very imperfect understanding of how bad things can get, and particularly where how bad things can get is a result of unforeseen compounding extremes. And so the idea is to develop a framework where you could suit up to actually have a computational environment to study that in a test bed. And I do believe that that is a key direction forward and something I would love to do.
Great. Always talking about, let's say, future direction, extensions. That was a question which is quite challenging, but I think we should have a short discussion about that. So again, you've been focusing on capital destruction, but how about like non-market impacts, especially related to biodiversity, ecosystem? Is there any modeling trick we might be able to use in order to look at the impact on those systems as well?
So the challenge is data, and I do know there's been a tremendous amount of work at CMCC and other European institutions to try to model natural capital and to introduce natural capital into the model. As we've seen from the description of the rolling plan model, the law of motion of capital in an economic model is extremely simple. It is an extremely simple discrete difference or differential equation that is linear. If you have something like a stock of fisheries, it's much, much, much more complicated. The dynamics are much more nonlinear. So one, there's a modeling trick, sure. We can get it into the model, but lest we go down the road of, well, you want numbers, I give you numbers, we have to think extremely carefully about the dynamics of that natural capital. What do the laws of motion look like? And then how will those laws of motion on what time frame be affected by the impacts that beset them? And the idea here is that's a challenge too, because in order to get this right, what we are talking about is a multi-capital model. You know, at the very least, it could be multi-sectoral, but at the very least, it will be multi-capital. And in particular, I want to draw attention to something that I mentioned, which is that natural capital in these models, even though it may evolve over time and have a law of motion, it is largely a fixed factor. The nature of ecosystems being very low frequency in space and time means that it's going to be subject to the magnification effect of extreme events. And then the question then becomes, how is that connected to the physical economy as we model it versus a non-market impact that enters directly into the utility function of the agent in the region versus other surrounding agents who might also experience it through a contact non-market process.
Thank you. So we've been talking about capital investments, but then a question that follows is who will be investing? So, and so this is more related. Can we think of extension that enable us to say something about the financial and maybe even fiscal implications of shocks?
Yes, so the paper that I referenced right at the end, Thakur and Kara, is a dynamic stochastic general equilibrium model, which actually has embedded within it Taylor rules. And one could adapt this framework, though it would be difficult to see, to understand optimal monetary policy rules, but one has to then introduce a stock of debt. And it's a question of whether the debt ends up being managed by the individual countries to whom various nuts resolves, or it's managed by the ECB at the level of Europe. But there are ways to do that. There's a literature on it, and I haven't really seen a lot of the SGE modeling coupled with these types of models, but ultimately they are dynamic models, and that is something that could indeed be studied. The question is as well how to calibrate it and how to calibrate it at high spatial dimension, how to introduce something like that. But it's certainly possible. We are already seeing in the intertemporal model the dispersion, the transmission of risk to areas that are not affected by the shock. And I admit, I chose a deliberately simple and predictable shock because that is exactly what I wanted to see. It's a natural experiment. How that then affects with debt, how it interacts with debt, how it interacts with monetary policy. These are all questions that I believe can be studied through introducing those elements in the model. The introduction is going to require some thought, some care, and lots of careful numerical calibration.
Thank you, Ian. I would conclude with one final question, and then, as we said already, Professor Sue Wing will be available, so you can reach him by email, and we will try to collect all the questions and also who posed the questions in order to get back to you. The final question that I just wanted to ask that was posed by our attendee relates to sort of the integration of this type of analysis, which focuses on climate impact with climate mitigation. So is it possible to integrate events and shocks that relate to the transition, to the energy transition, to the transition to a green economy? How would you see including these two different types of shocks in a setting like the one
A very good question, and I would say, lest I forget, I owe a big debt of gratitude to the WICH team for molding my thinking over many years with this. And indeed, this is a model that is very much like the WICH model, except that WICH and its precursor RICE are intertemporal models where the agents in each region don't really trade with one another except through trade in energy. However, with such a macro model, one could conceivably take a very simplified, because it will introduce a lot of computational complexity, a very simplified representation of the energy system and integrate it with the production function. So now that you're able to at least have the trade-off between carbon-based and carbon-free energy, and to see energy resources and emissions along with purely economic output. That in turn can facilitate the imposition of carbon taxes and moving to an integrated impacts and mitigation framework. And indeed, this is something over the very long term that's necessary because we are already in a phase of human civilization where we are going to need to adapt and simultaneously forestall through mitigation future catastrophic warming. So definitely those ideas are on the table, and it's just a question of time and effort and computational power.
All right, great. Thank you. Thank you very much. And thank you all for joining and asking questions. And I wish you a good rest of the day. And you will find the registration, the recording of the webinar on the CMCC website.
Thank you so much for having me. Have a good day. Bye.